Uh, in today's session, we'll understand DC motor modeling, mathematical modeling of DC motors. In order to design any controller or observer, for us to design observers or controllers for DC motors, we need to understand the mathematical model of DC motors. In fact, to design a controller or observer for any type of motor, be it a DC or an AC motor, its mathematical model, it's the concept, the understanding of the mathematical modeling of the motor is very important. We know this is basically just a recap of what previously has been done. We have the two uh, approaches that can be used to mathematically model a system, a transfer function approach and a state space approach. Uh, let's take a case of a separately excited DC motor. We have the windings, voltage Vt is applied, a current armature current Ia starts flowing, and we have the field circuit. As discussed in the previous class, there are two approaches of speed control in uh, DC motors. One, either by controlling the armature current or armature voltage, and the second method will involve the control of field current or the field voltage. So the mathematical model will also be based upon the armature control method and the field control method. So once we are going for the armature control, we keep the field circuitry constant, we keep the field current constant. Once we approach the speed control by means of field current control, in that case we keep the armature current constant. So once we also mathematically model a system, we assume if we are uh, controlling the voltage, controlling the speed of the DC motor by armature method. In that case, we consider the field current to be constant, the field circuitry to be constant. In another scenario, we'll consider the field circuit control, the field current control. In that case, we'll keep the armature current of the machine constant. Now, these are the for this machine, the electrical equations can be put as Vt is equal to RAIA plus LADIA by dt plus the back EMF EB. Whereas for the field circuit, we'll be having Vf is equal to IF RF plus LF DIF by dt. These are the electrical equations representing this system. In a similar fashion, we can have the mechanical equations. We'll have a torque induced in this armature, and there will be a speed, a rotational speed omega. So the mechanical equations can be written as J d omega by dt plus b omega is equal to the torque induced tau. So the torque induced tau will be equal to j d omega by dt plus b omega, where j actually represents say the inertia constant and b represents the viscous friction coefficient. There are actually three different types of friction coefficients. We are only assuming one type of friction coefficient, that is viscous friction coefficient. So now to model this motor, we'll assume in first case the field circuit is field current is constant and we are controlling the motor through armature current control. So in that case, our armature, the electrical equation of the armature circuit is Vt is equal to Ia Ra plus La dia by dt plus the back EMF Eb. We know this back EMF is actually proportional to flux phi as well as proportional to omega, the speed of rotation. So therefore we can write Eb is equal to Kb times phi omega. Now since we are assuming that the in this method we are only concerned with the armature current control, we are assuming that the field circuit, the field current is constant. That means the flux produced by the field circuit will also be constant. So that can actually be clubbed together with Kb. So in that case scenario, Eb will only be equal to Kb times omega. So we'll have this equation rewritten as Vt is equal to Ia Ra plus La dia by dt plus Kb times omega. So this is equation number 1. Second equation, that's actually the mechanical equation. Torque induced is J d omega by dt plus b omega. Fine. Here we have torque induced is proportional to the armature current, that is Ia. So it can be written as torque induced is equal to Kt times Ia. So we can rewrite this equation as Kt Ia is equal to J d omega by dt plus b omega. So this is our equation number 2. So equation 1 and equation 2 actually represent the mathematical model of the armature current control of speed control of the DC motor via the armature current control method. Now we can model this equation 1 and 2 either through a transfer function approach or through a state space approach. If we are we are adopting a transfer function approach, we'll actually what we'll be doing, we'll be taking the Laplace of equation number 1. So Laplace of equation 1 gives us Vt times S is equal to Ra Ias plus S La dia by dt. Laplace of dia by dt is S times Ias plus Ia0. Since we are assuming in the transfer function approach that all initial conditions will be 0, so we can say Ia0 will be 0. So initial conditions assumed equal to 0 plus Eb. Instead of Eb, we actually have Kb times omega now. Kb times omega. Since omega is a variable here, it will be varying with respect to S as omega s. and by taking the Laplace of equation 2, yields kt IAS plus is equal to J S omega S plus B omega S. Fine. So this is Laplace of equation 1 and this is Laplace of equation. So equation 4 gives us actually this is equation 4. IAS is JS plus B omega S divided by KT. Now substituting this equation number 5, substituting equation 5 in equation number 3, we will be Vt S is equal to Ra plus SLA. Instead of Ia we have Js plus B times omega S divided by Kt plus Kb omega S plus Kb omega S. I am taking actually omega S common. So this is omega. So since omega is the output, we actually need to find out omega S divided by Vt of S. So that will be Kt Kb divided by Kt divided by Ra plus SLA Js plus B plus Kt Kb. On further, we can open this up. This will come out to be as will come out to be La multiplied by J S square plus, let me write it here, Kt divided by J times La S square plus Raj plus Lab times S plus Rab plus Kt Kb. So this is omega S divided by Vts. So this is a transfer function. Using transfer function, we can find out the Laplace of output or Laplace of input equal to this. Now using the same equations, equation number 1 and equation number 2, if we have to model them using the state space approach, equation number 3 and 4, we have equation number 3 and 4, we have equation number 1 and 2. Using equation number 1 and 2 and assuming let us assume that IA, that is the armature current, is one state of the system and as it is dynamically varying in the system, and omega, that is the angular speed, is the another state variable x2. So using equation 1, we will be getting Vt is equal to Vt is equal to IARA. IA instead of IA, now I will be writing x1 plus LAD dia by dt, that's dx1 by dt, that's x1 dot, plus kb times omega. Instead of omega we have x2. So from this, x1 dot comes out to be minus ra by la x1 minus kb by la x2 plus vt by la, where vt is actually the input. So instead of vt, I'll be writing u here. 1 by L times ut. And using equation 2, we will have ktia, torque induced ktia, instead of I we have x1 is equal to j d omega by dt, that is x2 dot, plus bx2. So which gives us x2 dot is equal to kt x1 divided by j plus b minus b x2 divided by j. So using x1 dot and x2 dot that we have obtained, x1 dot and x2 dot, we can using equation above, this is say for example this is equation A and this is equation B. So using equation A and equation B, we can find this matrix that relates x1 dot with the output u. So x1 dot is nothing but minus Ra by La x1 minus Kb by La x2 plus 1 by La times u, and x2 dot is Kt by j minus b by j x2 plus 0 times u. So this actually represents the state space model, and if we are concerned with the speed as the output, so we'll be taking y matrix as 0 times x1 plus 1 times x2, so that will give us output as the speed if we are concerned with the armature current. So this is actually for speed control of DC drives. We'll be using the above two mathematical models, that is the transfer function model and the state space model that we have derived. They can be used for speed control of DC motors. If we are concerned with position control of DC motors, we'll have to replace omega by d theta by dt. That will give us the equations will change as Vt s. Vt will be now equal to IARA plus LADIA by dt plus Kb times omega. Instead of omega, we now have d theta by dt, and another equation, that's k. The mechanical equation will be ktia is equal to j d omega by dt. So we'll be having d2 theta by dt square plus b omega, that will be d theta by dt. So by taking the Laplace of equation, this is now the new equation 1 and 2. By taking the Laplace of equation 1 and 2 and then substituting the resultant of this Laplace of equation 2 in equation 1, we'll get theta s divided by Vts. We have derived omega s by Vts initially. Now we'll be getting theta s divided by Vts. That will be equal to Kt divided by RAJM RAJS square RAJS square plus RA plus RA B plus KT KB RA RAB plus KT KB. Divided by RA times S. So you can actually take the Laplace of equation 1, take the Laplace of equation 2, substitute IAS obtained from Laplace of equation 2 in the Laplace of equation 1, derive theta is by VTS, and hopefully it will come out to be this equation. And similarly, equation 1 and 2 for to obtain the state space model. Now these equations 1 and 2, also assuming the three state variables now as x1 equal to IA, x2 is equal to omega, and x3 is equal to theta. We have three variables in this system. Initially we had assumed only a speed control system, that we are not taking position as a variable. Now for a position control system, position is also a dynamic variable that we have taken into consideration. Equations x1 and x2 can be modeled in the same fashion, while as equation x3 dot, that's theta dot, is nothing but omega, that is x2. So what we'll be getting here is x1 dot, x2 dot, x3 dot minus RA by LA minus KB by LA, KT by J minus B by J, minus RA by LA minus KB by LA, KT by J minus B by J. They are not dependent on the third variable. X3 dot is 0, 1, 0. X1, X2, X3 plus 1 by LA, 0, 0 times U. And now in this case, if we are concerned with position as the output, we'll be taking 0, 0, 1, x1, x2, x3. So these are the transfer function models and the state space models for the speed control of DC motor drive and for the position control of DC motor drive, while assuming that the field circuit is constant. So mostly we'll be adopting armature control methodologies, widely adopted as compared to field control method. We tend to control the armature voltage of DC motor through power electronic devices. We do not go into the field current control of DC motors. So these modeling, so this is a mathematical model of these drives, that of the DC motors, that needs to be as we move forward, as we study the drive systems, as we model the controllers and observers for DC motor drives. These transfer function models and state space models will be required for analysis.